So you don't have anything to discuss? We can go to the next topic. Okay. I don't know if any Christian is here. Like it's a Christmas day, right? So at least in Canada, it's like we celebrate a lot and it's holiday. Like this is the only time we get holidays in Canada. University is fully closed from 24th to this time January 5th. Like you don't have anything for like 1 week. So okay, so today mainly we are going to focus on multi-sensor filter. Like so far we talk about how to do tracking with single sensor. Today, like that, this topic itself is a like real complicated topic. At least we will try to cover the basic part of how to use multiple sensors to track targets. Okay, so when we talk about multiple sensors, there are like two architectures that we can use. One is the centralized architecture, and other one is the distributed. This one, actually not going to talk too much about that. Don't worry about that for now. First half, like around 1 hour or so, we will talk about this. Then we will move to this. Okay. Centralized tracking means you have sensors, multiple sensors. They send the measurements to the tracker. You can say the tracker that views all of them and gives a track. Okay. That is called centralized tracking. So we are going to talk mainly about that first. Later on, then we will talk about how to fuse the track. This is also track. This is also track. Then how to fuse the tracks. That clear? So that is our objective today. So we are going to start with multi-sensor fusion. I go back to the previous slide. So this is the multi-sensor problem. So slides might be a little complicated. So I will just okay, so now we are going to talk about multiple sensors. Multiple sensors could be any type. So we will have two type of case. One is heterogeneous, other one is homogeneous sensor. Let's consider in a general case, which you have seen, you have a radar and an angle-only sensor. Okay, let's assume we have two sensors. One is a radar, other one that gives angle only. So you know radar means that gives R and theta. This gives theta. Okay. And let's say sigma R is 10 meter and sigma theta is 1 degree. This one says sigma theta is 0.5 degree. So clear? Sigma means standard deviation, right? Measurement standard deviation of angle only is assumed smaller than radar angle measurement. This is what we have as a sense. Two senses. Okay. And let's say their sampling time, say this is 2 seconds, and say this is 3 seconds. Okay, so now we want to do the tracking. So that means you give only one track. One track means one tracker produce the track by combining all these measurements inside. Okay. So now let's consider the time frame. So if you see here, slide, we say there are two approaches to do multi-sensor fusion. One is sequential update, other one is parallel update. Okay, I will explain both of them, but I always use this one. Okay, I would recommend you to consider sequential update. Parallel update has some benefit, but it can be used only in certain cases, not always. Okay, so that first of all, let's talk about that. Synchronous versus asynchronous. Okay, synchronous case and asynchronous case. Synchronous case means, say, if you have think about a time axis, this is time. Say the sensor one produce the measurements here. Okay, this is sensor one. And sensor two give the measurement exactly at the same time. This is called synchronous. Both sensors are synchronous and they provide the measurement exactly at the same time. Then, in this case, you can use parallel update. Sequential update or parallel update. Both are possible. Okay? But, so let's say this is a case. Then if this is a case, what are the key values? This is k equal to 1. This is k equal to 2. K equal to 3. K equal to 4. K equal to 5. K equal to 6. Are you okay with this? Right? This is the normal karma with the time step. Now, I'm going to talk about general case. This is a kind of ideal situation. Usually, you won't have some situation like this.
So what is sequential?
Sequential and parallel. I will explain. Okay. Now, if you consider this radar and angle sensor, sampling time are 2 seconds and 3 seconds. In that case, if you plot the same axis again, time. Say this is radar. Okay. Now, if we have angle on a sensor, say that initially say that gives here, 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 here. Is that okay? Because one is 2 seconds, other one is 3 seconds. So they are providing the measurement at that time. Okay. Now I'm going to talk about sequential update. Then later on, I will go to the parallel update. First, we are going to talk about sequential update. In that one, the k, the value of k is like that. K equal to 1, k equal to 2, k equal to 3, k equal to 4, k equal to 5, k equals 6, k equals 7, k equals 8, k equals 9, k equals 10. You understand this part? This is the sequence log. Okay, that what I do is I have tracks. First, I take the radar measurement. I don't care about the angle only. Update it. After I update that, I get a radar angle only measurement. I consider as a new sensor that gives input. Update. So that becomes K2, and so on. So this is what we would do in the sequential update. Okay. So now if you think about, so this is a tracking problem. So that includes data association, everything. But for now, just to simplify the discussion, assume this is a filtering problem. Let's say you don't have a clutter or anything, just filter it. So think about Kalman filter. How do we handle this? Kalman or extended Kalman filter. How do we handle that with an extended Kalman filter or Kalman filter? So what we do is, and let's start with the tracking problem first. So we want to initialize track. How do we initialize track in this case? One simple approach usually we can do, but that's not an optimal way. You initialize track only with radar. Initialize track only with radar, but update with radar and angle one. With one simple solution. Because angle only, you can't initialize track with single angle or sensor. Right? So what we do is we initialize the track only with the radar, and angle only sensor helps to update the state. Okay. So this is what we can do. So I see now whenever we do that, whenever radar comes, we associate whichever is not associated, creates an interruption. Okay. Now when it comes to update, so when I said k equal to 1, right? With the radar, say I update that x1 1, so 1 and 1. 1 and 1 is updated, and you have p 1 and 1. Okay. So this is arc updating with the radar. Now, what is the value of t that you would use in this bit? So you want to go from 1 out of 1 to 2 given 1. What should be the t that you would use in the Kalman filter? In the Kalman filter, you know that you would use an f, right? You would use an f in the Kalman filter with 1 t and so on, right? What should be the value of t that you would use when we go from this time step to this? 0. Is that right? T should be 0. That means what? This equal to this. And the predictive covariance is also the same. No noise. No Q. Okay? Make sure that your Q calculation also involves T. So that means when you set T equal to 0, Q becomes 0. Otherwise, that's wrong, right? Because you won't have any noise at the same time. Okay? So what we do is the prediction is same as this. Then you get the angle limit, right? You find the nonlinear edge or linear edge and you use ATF and update. Okay? Then what do you do? Then you go here. In this case, what should be the t value? T value should be t should be 2, right? 2. That's 2. I think 2, right? That's 2, right? So with 2, you go here and update with the radar. Then you use t equal to 1. You go here, update with the angle only, and continue. Okay. So at this point again, so when you reach here, again, you go this way. Go here, then here. Right? So this is the sequential update method. So that way it's easier as long as you write your code such that it's not hard coded for a particular sensor type. If it's two radar, that's easier because type is the same, only the parameters are different. But if it's a different type, in the code you have to properly write, okay, if it's a radar, do this, if it's angle only, do this. Okay? And if you do this, this is the sequential fusion of sense. Fusing one by one. Okay? But I just talk about the filtering problem. But if you think about tracking, so as I mentioned earlier, so we whenever radar measurement comes, we associate, update, and with the remaining, I will add the new target. When the angle only sensor comes, I do the radar association, then use the associated measurement to update. Is that clear? Any question on that? This is a basic, right? It's a basic of using multiple sensor sequences. But the coding wise, it's not, it's hard. Okay, so you have to write a code. But even the code I have given, if you want, you can modify the code such that it can handle multiple sensors. Basically, if you have a for loop, and then yesterday we had a for loop for k, right? K equal to 1 to k. So you find a sensor type, then do the update with that particular sensor, right? So that case, so the next k, it could be radar or sonar, you do that. And but only difference is that in that case we assume k always 2, but in this case you can't assume that. You have to calculate the t based on the last t last and t current. So you update that, right? In order to find that, usually what I do is, so I know there's like 2, 4, 6, 8. Other one is 2, say 5, 8. So that we have time for and find the next time step. So we know that the minimum of 6 and 5 is 5. So that becomes the current time. Right? So you do that sequentially. Okay? So that's all about sequential update. Now I'm going to talk about parallel update. Parallel update is possible only if this is a case. Okay, all the sensors are coming at the same time, or even in this case, whenever both comes at the same time, you can do the parallel update. Okay. For the parallel update, the data association has to be done properly on the normal way, but the parallel update usually for filter. The sequential update, what we do is, we assume that equal to r theta, and then we do the Karman update. Okay. Then we have another that is theta. Then we do another Karman update. Is that right? That's what we do in the Karman. The sequential update when both of them comes at the same time. Now let's say in the parallel update, what we are going to do is you are going to create a pseudo sensor, assuming that is r theta and theta 1 and theta 2. With this one is sigma r of 10 meters. This is sigma theta of 1 meter. And this is sigma theta of 1 degree, 0.5 degree. And this is from radar location. And this is from sonar location. Because you need the sensor location also when you find that, right? So what we do is, instead of doing two counter update, we are going to do only single update by fusing these two. That seems like you have a super sensor that give both of them. Okay, so once you combine these, what do you need to do? So you think that if you H1 here, linear H2 here, then this guy. Something like that, right? So that pseudo sensor is providing this measurement, and the measurement equation is stacking both of them. And the R is also R star, also like that, right? Sigma R squared, sigma theta 1 squared, sigma theta 2 squared. Okay? Then after that, this is the normal Kalman filter problem. Once you formulate like this, you update with the normal Kalman filter. Is that okay? Now the question is, which one is better?
The times are different. Theta 1, theta 2.
The times are same. I said that you do that. Yeah, so when we get this, we can't do this. I'm talking about only here or here. Otherwise, this approach cannot be done. That's why in the slide also it says If this is a synchronous case, then you can use it. If it's asynchronous case, you always have to go with the sequential update. That is given. So there's no anything that you can do about that. Okay. So if you go through the slides, sequential update, like anyway, this math, like the sentences might be complicated, but these sentences talks about what I explained. As long as you understand that. So I explained with the two sensors, but this could be any number of sensors. Okay. Any number of sensors, any type of sensors could be the same type, different type. That's fine. Okay. And this one says synchronous case and sequential update. This one says you do the counter filter without prediction because the t is 0, so you don't need to predict. So you update with one of them, take that one and update with the other. Right? So this is what basically we do. If you have n sensors, we have n sensors and all of them report at the same time. In the sequential update, what we do is we update the track with that sensor, predict from T1. This is asynchronous, sorry, asynchronous, not synchronous, right? So we predict from T1 to T2. Sometimes this could be the same, so it could be 0, right? Predict there, update, and so on. We continue. Okay. Okay, this is where I think we have a quiz question tomorrow, a quiz question on exactly on this one. When to use, oh, not very. I already told you, right? I always sequential update. Even if you want to implement something for multiple sensor, I recommend sequential update. But there's a benefit of parallel update. Okay, why? When would you? Oh, what is the benefit of using parallel update over sequential? Right. So which one is computationally efficient in terms of filtering? What do you think? Which one is parallel is computationally efficient? Why do you think so?
Sequential time track was key.
Pardon?
Sequential, you have to keep the time tracking. Time to keep in track, but that remains smooth.
So the difference between sequential and parallel is that sequential you do 2 farmer with update, and this is parallel you do 1 update. So which one is faster? Parallel is faster. I thought sequential is faster. I can't easily say, but the reason is that finding inverse of 2 by 2 matrix is faster than finding 3 by 3. So that gives, like when you have 3 by 3 matrix, so doing 2 by 2 and 1 and might be faster than doing 3 by 3 inverse. So, right? So because of that, especially if it's 2 by, okay, if you have multiple sensors, like 10 sensors, finding the inverse and multiple matrix multiplication and so on with 10 by 10 is slower than doing 2 by 2 10 times. Okay, because of that, parallel update usually, in my opinion, slow. Okay, little slow. Okay, so that, and also it has a lot of complications. So then why do we want parallel update? Okay, that is why it says here. Let's say we want to use sequential update order. Which order to use? So in this one, like when we see this, I say this is the time axis, and this is radar. This is angle. This is radar and angle. So which should be the first one to update? So if you want, I can say k equal to 1, k equal to 2, k equal to 3, and k equal to 4. I can say that, right? Or I can say k equal to 1, k equal to 2, k equal to 3, k equal to 4. Correct? So, which one is better? Should I go with this first or this first? That is a question we need to answer in the sequential update. Usually, even in my tracker, I don't do that decision. I just simply go with the first sensor. That may not be optimal. That's okay, but small error direction might be there. So it says that, okay, that's what it says. In the sequential update, for nonlinear measurements, so for nonlinear measurements, but for linear measurement, order does not make any difference. But if it's nonlinear, then order matters. Clear? So if you have a sensor, two sensors, both of them are linear. But most of the cases are nonlinear. Radar is nonlinear, angle is nonlinear. In that case, it says that if it's linear, it doesn't matter. You can pick whatever the sensor first and no problem. It says if it's non-linear, then order matters. And it says that better to update with a sensor with more accurate sensor. That itself is little harder problem. Reason is that when you do the extended Karnaugh filter, the nonlinear filter, you do some approximation of age respect to some point. That approximation will be different. Okay, so what you need to know here is that in the sequential update, if you change the order, you make it slightly different output, not exactly the same output. So you first update with the radar, then update with the angle only sensor, or you update the angle only sensor and then they update with the radar. Output won't be exactly the same, slightly different. Okay, that is when the parallel update helps. In the parallel update, because you stack both of them and update at the same time, you don't decide the order. So it says that if you do the parallel update, the results will be better than doing the sequence update because of the nonlinear. If it's linear, both of them, sequential and parallel update, will give the same answer. If the measurement model of both sensors are linear, order doesn't matter. So whether you update with the radar, it's actually linear, and angle only, get the results and go with the other way, both will have the same results. You do the parallel update, you'll have exactly the same result. But if it's a non-linear case, one sensor, both are non-linear, then each of them will have different results. Let me repeat that again. So you have two linear. You have two linear, say linear sensor 1 and sensor 2. So in this case, the sensor 1 first and sensor 2 first, you get the results 1. In the other one, you have sensor 2 first, sensor 1 second, and you get results 2. In the other one, both are done together as a parallel and results 3. So as long as that sensor 1 and sensor 2 are linear, all these are equal. Okay, that's the first conclusion. Second conclusion says, if it is S1, S2, then S1 again, S1, S2, R1, S2, S1, R2, and S1, S2, R3. As long as one of them is nonlinear, this is not equal to this, and this is also not equal to that. None of them are equal. So in this case, they say that this is a little small, slightly better than this when we have nonlinear. Okay. So that is the theory part. But in my personally, that difference is small. Okay, it's not worth for the hustle that you need to make in order to do the parallel updates. The reason is that parallel update is about filtering problem. But before that, you have to do the data association. Data association is a harder problem. You have to update, associate with the both radar and the angle only, then you fuse. Okay, so at that case, you can stack both of them. Okay, so if the quiz question asks you, what is the benefit of parallel update over the sequential update, what would you say? So when we fuse nonlinear sensors, right, in an synchronous case, parallel update gives slightly better performance and that nonlinear the sequential update, because in this case order doesn't matter, the other one order matters. That's the reason. Okay. This one simply talk about what I said. So this is what happened in the parallel update, right? So we stack all the measurements that we get, sensor 1, sensor 2, and sensor n. Then you form this edge by stacking all the edges, the linear edge, and the R is also stacked. Now you consider this as a super sensor that gives one measurement instead of n sensors. Then you do the normal count update. Okay, so this is the next problem. So we are now done with the centralized sensor fusion, and we discuss about how to use multiple sensors with the tracker. Okay, implementation we need additional thinking and writing, but other than that, the overall idea is this is the overall idea. Okay. Okay. Next, we are going to talk about outer sequence measurement, but I don't want to spend too much time here because it's a complicated topic, and also you don't need to handle this in most cases. But anyway, let me introduce it. You should know that at least a terminology. From the name itself, can you guess what's the meaning of outer sequence measurement? Anybody? So outer sequence measurement means that there is a single sensor. Usually outer sequence measurement comes in with multiple sensors, but for now single sensor, I see single sensor. And this is the time axis. Okay, so this is k equal to 1, k equal to 2, k equal to 3, 4, k equal to 5. So now you have x hat 5. Are you okay with this? The normal converter we have updated up to this point. The normal case, what do you expect? The normal situation, you expect the measurement to come over here. Are you okay with that? Correct? Usually it come over there. But in the outer sequence measurement, for some reason, the measurement generated at this point come at this point. That is called outer sequence measurement. You get this? The measurement was generated at this time, but it comes there at a later time. So usually this could happen due to the communication delay. Right? For example, if it is routed to different routers and it's coming, the data coming, so that measurement comes later. So how do we use that information? That is called outer sequence measurement. Measurement comes in an outer sequence order. What to do with that measurement? For example, say you have a trajectory. That trajectory is going like that and somewhere here. Okay. So this is the current time. I'm here. But somebody says that, so they say this is like now 9:47. Say at 9:47 it says that I am here. But some measurements say that at 9:30 this person was somewhere here. Okay, that is outer sequence measurement. So we will keep on updating, but this report came later, but it's about the location at this time. Now our objective is to use this information to update this state, not this state. Okay? So our objective, that is the main thing in the outer sequence. My objective is that, can I use this information to improve my current estimate? Not about the past estimate. So my objective is that at this one I have a P. Can I reduce this P? P is a covariate, right? In the tracking of filtering, the objective is to reduce a covariate.
During that time, updation, during the updation at 9:30.
Pardon?
During that 9:30, I am updating my column.
No, so that's what I'm saying. You are not updating column filter. You get a measurement at 9:30. What to do? We are not sure what to do yet. Because you can't use a Kalman filter, because in a Kalman filter, you can do that only if your previous state is somewhere here. If the state is here, if you think about T, capital T is like a negative value, right? Time. So that you can't handle with a normal Kalman filter. So you don't update with the Kalman filter. Now the question is, if some here, how to use this information to update this information? That is the outer sequence measurement. Okay? Okay, now let's think this way. And another measurement comes at the same time. So at 9 o'clock, I was here. Which one has more information? One is right now at 9:47, we have an estimate. Now I get two information, additional information. Saying that 9:30 I was there, 9 o'clock I was there. Which one out of these two measurements, which one has more information or that helps to improve your current estimate? Neither is better, right? Is that right? The reason is that because of the process of height, this information may not be relevant at this point. If the capital Q is 0, then both may have the similar information. So there's no uncertainty. You can predict and come to that, right? So that means what you see, when this gap increases, the benefit of this in updating that definition. So after a certain point, I can throw it away. I don't need to go through a hard update step. I can throw this away. Sometimes I think, because if I show the outer sequence measurement update equation, that's complicated. So one simple solution might be always throw it away. Because if this is going to happen rarely, like say if you have 1,000 time step, say let's say this happens only 2-3 times, then throwing away that is fine. But you can't do it like either you have to update using proper outer sequence measurement update or throw it away. By throw it away, you lose some information, that's still okay. Okay? So that is the outer sequence measurement. Now, again I repeat, I don't want to update the state at this point. I want to use this information to update at that point. Now question is, how to do it? Okay? That is for outer sequence measurement. Okay, as a first thing, when it comes to outer sequence measurement, you may need to understand the notation. This one says we already have this estimate at K. Now you are getting a measurement at kappa, so that's what I said. This is K and this is kappa. Okay, small k. So when you have an update at this point, you have a measurement originated at this time. But what you want is, you don't want this. You want A given A comma kappa. Okay. So what it does a notation. This means you want to update this state. We don't care about that. So this is like a smooth thing going back in time. We don't want this. Okay. What I want is, I want to improve my current estimate. I want to improve my current estimate using all these measurements plus this outer sequence measurement. Okay. So that is what we want. This is what it says. So we want to have this. Okay. So this is what we want to estimate. So, okay, this is little complicated equations. Okay, now we are going to talk about two different cases. One step lag, other one is the multi-step lag. Okay. So we have two cases, one step lag and one step. The meaning is that if you are here, if the measurement comes from here to here, this is a one step lag. But if the measurement is somewhere here, then that is called multi-step. Are you okay with that? From the name itself, it says that you had measurement here, 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 and here. Then you get an outer sequence measurement that was generated between these two, called as a single step lag. Okay, the lag is less than one step. In the other case, it says that if the measurement was coming from this, we got few updates before that, then we call that as multi-step lag. Okay, the name itself. Because the algorithm to handle this one is different from algorithm to handle this. That's why we have two different cases. In the single step lag, one step lag. Okay, before that, this one. Earlier I said that you can throw it away the outer sequence measurement and you can live with that, right? But under certain conditions, you can't do that. Okay, one example of this is that as if a radar is rotating like this, we have another radar here that rotates like this. Are you okay with that? So we have two radars. This is radar 1, this is radar 2. They rotate like this. So let's say it rotates at time 10 here. When it comes here, say 10.25, 10.5, and 10.75, something like that. It's okay. That's how the rotating radar works. And for the other one, say this is 10, 10.25. Are you okay with that? So if you have a target over here, first sensor will detect at 1025, other one will detect at 1075. Correct? Because it's a rotating radar. Now let's say that in the sequence update, you are using this as a first sensor. Okay, so that means you update the target at 1075. Then you go to this radar. The measurement comes from 1025. This is not real outer sequence measurement, but the way we do the sequential update, it introduces an outer sequence measurement. Is that clear?
So you get 10, 25.
Pardon?
First it is like both are centralized at one place. First I get as a time part before will come first, then I get the first. After that to 10.75.
No, this way, like, see, this is what happens. The sensor one gives the measurement. Say, I think that's the sensor one, gives measurement that has values like 10, 10.1, 10.25, and so on, 10.75, and so on. Okay. Then sensor 2 has again some 10, 10.08, 10.25, and so on. Right? So this is one frame. For us, it's a whole frame in the rotating radar. Okay, so that's all you know. Now, let's say you update the track with this. Okay, so out of these, I'm saying this is the measurement corresponding to our target one. Okay, so that means in the sequential update, when we use all these, target one is updated with this time. Right? So now we have the updated stage x k given k at t equal 0.75. Are you okay with that? Now we want to update the second sensor. When we do the data association, we find out that this is a measurement comes from that target. So now we have a situation in which our current time is 10.75, but the measurement time is 10.25. Okay, so that Carnot filter cannot handle that problem because t is negative. Right? So even though there's no real outer sequence measurements, the way we do the sequential update, it just introduce the outer sequence. In this case, if you throw it away this measurement, then you won't use a sensor 2 at all. Radar 2 measurement, you are throwing it away all the time. So at that point, you have to handle the outer sequence if you want to use it. Okay, so if you guys are real world people and then if you're using rotating radar, this problem is always going to be there. Okay. Okay, now I'm not going to spend too much time on that because these are the equations. Right? The derivation is hard. You don't need to worry about that. It's similar to karma vector. You don't derive the karma vector. Similar to that, people are given the way to update with the outer sequence measurement. So what we do here is that first you find the inverse of going in that direction and we multiply by that. So this gives the kind of predicted. You predict the state from here to here. And so this is a little complicated. Okay, I'm not going to spend too much time here. So you go back to that. Then you find some matrices similar to the karma filter. And then you find some weight. Eventually, you update this state using the current state, last state, so updating this weight, given the difference between the last measurement, the outer sequence measurement, and the predicted outer sequence measurement, and this weight is coming from that time step to this, it comes to this. Okay, that is intuition, but it's a little complicated. The whole thing is harder to understand. But anyway, this is how you would handle the outer sequence. Okay. So let's talk about how to handle multiple steps. Multiple steps, there are two approaches to do. I am going to just talk about only one approach. Okay. So this approach is really an interesting approach. You can use that not only in the outer sequence, in some other cases as well. So that is what I want to talk about that. So now we want to handle a situation in which measurement comes here. How will we update? We know. Okay, now let's assume you know how to handle this. If you have this, we already talked about the equation. You know how to use that to update. Now, if the measurement comes here, how to handle that? In order to handle that, we are going to talk about equivalent measurement update. What is the meaning of equivalent measurement? That is, I said, interesting thing is this. equivalent measurement. Okay. In the equivalent measurement, what we are saying that okay, in the equivalent measurement, let's say you have a situation like that. This is the idea of equivalent measurement. Okay. So in the normal case, so you have one measurement here, another measurement here, another measurement here, another measurement here. You get it, right? Okay. So that say, let's say you have x hat, okay, 5, 5, 6, 7, 8, 9. Okay. You have x hat 9, 9. Okay. So you have that. Now, so we have like set 6, set 7, set 8, set 9. Are you okay with it? This is a normal filtering of it. Okay. So we have a state here and then we get it back. Idea of equivalent measurement is that we are going to summarize all these with another sensor, I would say, like that. This will give the same output as that. That is the idea of equivalent measurement. That means, let's say, instead of using those 4 measurements at different time steps, you just use this measure, this state and that measurement, you get the exactly same output. That is the idea of equivalent measurement. Clear? So you want to find one measurement that is equivalent to have all these 4 measurements. Information wise, the same. So instead of using those 4 measurements, if you use one measurement, you get the same information at the end. Okay? That is the idea of equivalent measurement. How to combine this to say, we will talk about that. For now, assume that if we have 4 measurements, instead of those 4 measurements, you have one measurement, output is the same. So we convert this problem into this. Okay? So now we said that our outer sequence measurement comes somewhere here. So that comes here. Now what you see is that this was a multi-lag. Now this is a one-lag problem. You understand that? So we converted the multi-lag problem into one-lag problem by changing the problem itself. Then we use the same equation that we use for one lag. Okay. So now what's the remaining part? The remaining part is finding out this one. Right? How to come up with a sat star that gives the equivalent of that. Okay, that's the idea of equivalent. Okay, if you look at this, so this is what it says, right? So we instead of having all those measurements, we want to come up with a super sensor that gives this sat star with that. Keep in mind that this can be a different type. This also star. That means if this is a radar sensor, this does not need to be radar. It can be any set, any measurement. Okay, so this is if it is RF data, that does not need to be RF data. Okay, so that is one. So what we do is, as a first thing, to simplify this, we start with this. H is IND matrix. That means what kind of sensor is that? So we assume that the sensor is measuring X dot, Y dot, Y dot. Because that's like imaginary sensor, there is no actual sensor. So we Like arbitrarily put H equal to I because that's easier. If you want, you can come up with something else as well, but this is much easier. So we pick H equal to I. That's the first thing that we do. So this one is decided. This one is decided now, that is I. Now we want to find the R star and the measurement. So that gives the equal. How do we equalize that? To equalize that, we say this. Both covariants should be the same. The covariants that we got with those four sensors should be equivalent to the covariance we get with the single sensor, with single measurement. So we equal those two. Okay. With that, so that is equal to this. You already said H equal to I. So if you substitute that, so by and rearrange it, so we have the R. Okay. So we start with H equal to I, then we say that updated covariance should be the same. And by using that, we can find the value of R star K. Okay, now I answered this. This is done. Now the remaining part is what should be this so that it is equal. Okay. Then what you do? You use those and then you substitute all of them, you get the weight stars and you can get the innovation and so on. Then you use the single lag problem. Okay, so that is about handling multiple step lag with a single step lag algorithm with the equilibrium. Sometimes is you can use this equilibrium idea somewhere else as well, not only in the outer sequence measurement. As long as you understand this concept, you can put all these measurements together into one. That is can be used. I think even in the tracklet fusion, sometime we can use it. We'll talk about tracklets only, but this is the idea of fusion model. Okay. Okay, so that's all about this multi-sequential update and parallel update and outer sequence measurement. Next, we are going to talk about track-to-track fusion. So as I mentioned, so far we discussed about this. Now we are going to move to this. This is a little complicated algorithm. I would say that track-to-track fusion is much harder than measurement to measurement. Okay? But you can't avoid that. Okay? If you are working for industry, sometimes you have to handle that. Okay? The problem that we have is that in general case, let me handle the general case in which you have a fusor. So this gives the tracks. Another one gives the tracks. Another one gives measurement. You combine all of them and give the track. This is the global or a general fusion algorithm that can handle all kinds of systems. For example, let's consider this is the situation. This is the scenario. Okay? And this first tracker says there's a track here, and here. And this second track says it's somewhere here, and here. Okay? And then that measurement says, this measurement says, right? So now these are the information you have. Like you have information from three different sources. One source says the track is here, another one says track is here, and track is here there. And the red one is from one source, the black one from another source, and the blue one from another source. Okay. Now, how do you make use of that? Because like you can't make a decision with all these. Somehow you have to fuse and get the final out. So like maybe you would convert this. So this is an input to our fusion algorithm. final output that we want is from this, somehow, I want to say this is the fuse track, this is a fuse track, this is a fuse track, maybe this is a fuse track. Okay, so this is the input to be our fusion algorithm. The finally fusion algorithm will give it. Right? Then decision making will be made based on this, not based on that. So that is the idea of track-to-track fusion. Usually when we say track-to-track fusion, we don't talk too much about this. But in general case, you want to handle that as well. Okay, so but in normal tracking, like once you know track-to-track fusion, you can update the measurement and time. And that's not up. So this is a problem that we have now, how to fuse that. No, that you don't know. We don't know anything about that. That association itself, your problem. You have to decide whether you to associate or not. Sometimes, okay, you are right. So sometimes the tracker might say like that, right? Because like say these two are not associated, then tracker might say there are two. Because association is, think about real situation. How do you know they associated, right? So somebody gives this, somebody gives that. That's all given to you. Nobody is going to tell you that these two are coming from the same target. Nobody would say that. But sometimes say this one. Say this ID 1, 2, and 3. This one says 1, 2, and 3. So next we are going to talk about this problem. Track-to-track association. That's the first step that you have to handle. You can't use the IDs to associate the track. That's the first mistake. Usually some students make. So I would say that okay, I would associate 1 and 1, 2 and 2. That will not work because in one case you may have a false alarm. You create one, then the ID all the ID will be shifted. So you can't use the IDs too much, right? So for example, in this case, if you might see ID, then this and that will go together, right? So both trackers has the IDs independent. So you can't use the ID to associate the track. Okay. So how do we associate? Then this association should be similar to what we did with the track association, something similar to that. So we want to do the association first. Okay, first do the association, then how to fuse. Those are the two challenges we have. Okay. Okay, this is what the first slide it says, right? First problem to handle is track-to-track association. Okay. In order to solve this problem, we want to decide which track goes with which other track. Then track fusion. This is like a data association in the normal case, and this is like a common filter. Okay, so we want to do filtering or the fusion, and also we want to find the association between the tracks. Okay, that's the requirement that we have. Okay, so again, the quiz question is based on one of this slide. When we use which, say you go to a company and they don't have any system yet, but they have two centers. You have to decide whether you want to go with the centralized or distributed. Okay, you have to decide. If they give me an option, most of the time I prefer centralized. Okay, this is my option. The reason is that that's little easier to implement and optimal. Optimal. Okay. Then why people will go for a distributed case, right? I said that centralized is easier to implement and an optimal implementation as well. Then why do you worry about distributed? One reason is communication. So if you think about communication, so in this, say for example, if you have sensor here and sensor here, I think you guys are working on sonar and sonar voice, right? So that communication bandwidth is limited. If the fusion is here, so you may need to send 100 Z values. But instead of sending hundreds of Z values, you can send 2 tracks. or one track. So that way you can reduce the communication load. Okay, so you don't need to send all the false alarms to the comment. In this centralized one, you send all the false alarm and everything here, but in the distributed, you remove the false alarm, form the tracks, only send the track. That way the communication load is reduced. Okay, the benefit of distributed fusion is the less communication load. This is the only benefit of distributed fusion. Okay, oh. Only benefit of distributed is less communication. But centralized optimal, but heavy communication. In addition to these, the real world challenges is that some companies, if you purchase a radar or something, there are companies, they will not give you measurements. Usually you think that okay, if you develop a radar, you have the freedom so you can decide what you want to save and so on, right? But I work with real world people. Their challenge is that you purchase a radar that provides only tracks. They won't give any internal measurement to you, or you have to pay more to get the internal data. Even the autonomous vehicle, that's the case. They won't like, for some reason, they will not give you an internal measurement to you. I give only tracks. You do whatever you want. In that case, you are forced to go with the distributed fusion. Because you can't go for centralized fusion because you don't have access to the measurement. Okay, so that is one case in which you have to go with the distributed fusion. So now at least you can assume that you are convinced that you have to handle the distribution fusion at some point. Okay, and then for now, fusion is a complicated case. Okay, for now we assume both trackers are producing the same state. Okay, but in real world, like if someone is using this and another person is using that and that, then this becomes a harder problem. How to fuse two different heterogeneous tracks. That's how. So I'm not going to focus on that. For now, I see both trackers use the same state, then you won't use both of them. Okay, that is the objective that we have. So, okay, so then earlier I always said that you get tracks, right? Here also you have tracks. So there is another one called tracklet. I will talk about that shortly. So for now, don't worry too much about the tracklet. Focus on track. And the other one is the literature, they call it as AMR, Associated Measurement Report. Okay? So the difference between track and the Associated Measurement Report is that I said that so if you have a 100 measurements, you have 100 measurements, only 5 of them are real, 95 false alarm. Okay. So in the normal centralized case, we will send all these to the fusion node. Associated measurement report means this one has a tracker. Okay, this has a tracker and it produces tracks. Instead of sending these tracks over there, this will get the measurement that are associated and send this. Is it clear? So you have think about one system, one radar that produces 100 measurement. In the centralized case, we send all 100 measurements. But really, like if you know simulation, 5 of them are real, 95 are false alarm. But you don't know which one is real, which one is false alarm. Nothing is known. But this tracker, let's consider this is a radar on a ship, and you want to send this to a ground station. Okay, So from the ship, you can send 100 detection to the ground station, and so ground station can process that. Or on the ship itself, I have nearest neighbor CMKF. Okay, that filter tracker is running. So I produce some tracks. So I can send the tracks. That is one approach. Or instead of sending tracks, when they have tracks, you have associated measurement, right? So this is what I say, right? So I said that. So this is a track. So you have a ellipsoid. This is a track, and you have one measurement here and here, for example, and then here. So the associated measurement might be only this, and then if you want, you can send this as well. Because you know that others are like false alarm. So you are going to send only the measurement that are associated to the tracks. So that will reduce the communication load. That's the only thing. Reduce the communication load. So associated measurement report means you can think with somehow you eliminate possible false alarms and send only the reduced number of measurements.
Confirmed tracks less. Tentative tracks.
Confirmed, but that's up to the user to decide. So confirmed track is less communication, but if you send the tentative track also, then maybe you can reduce the latency at the global level, right? Okay, that's you can consider as a tuning parameter. You can say whether we want to send the associated with the tentative tracks and so on. Okay. Then the other problem is that the communication between the fusion sensors could be asynchronous. That is the other case. That's a usual case, right? Similar to the multi-sensor. Centralized fusion, this is a time axis, this is time. This is a track from track 1. You get tracks here. One case is like this, track 2. This is called synchronous. All the tracks are recorded at the same time. In the another case, and then this is a more generic case. This is what usually happens. That's T1, and T2 comes here. Okay, so this is called synchronous communication. It is asynchronous communication. I would say in the real system, unless you do simulation and do that, this is a normal case. Okay. Now we want to see how to handle that. And I will spend some time on this as well. Fusion could be performed with and without memory. As I mentioned, the fusion itself is a harder problem. I won't, that 1 hour is not enough to handle everything, but at least I will introduce the problem, then you go and read more on that. So this is one of the problem with and without memory. I always implement with memory, but if you want, you can implement the other as well, but I will talk about that. Other one is, this could be done with and without feedback. Usually I hate feedback. Okay, I don't want feedback. Feedback means this. In this figure, if you zoom this, there's a dotted line, right? This is a feedback. This is the feedback part. That could be an optional one, but if the feedback is here, then the problem becomes even harder. Okay? In the track-to-track fusion, the main problem is the correlation. How to handle the correlation properly. If you bring the feedback that introduce more correlation, that problem becomes hard. Okay? I will talk about the correlation, then you will see why this is hard. Okay? We can take a short break, a 10-minute break, and